Okay, good afternoon, everyone, or good morning, depending on where you're connecting from. Today, we are very happy to welcome Paul Tackley, Professor of Geophysical Fluid Dynamics at ETH Zurich, who is going to talk about self-consistent generation of tectonic plate boundaries. And this is very much aligned with what we've been running all this year in our geodynamic GEO at EAIFR series. And so, yeah, we are very happy. So, Paul, the floor is yours.
Okay, well, thank you, Catherine, for the invitation. And I'm happy to present some of the research that we've been doing. So yes, the focus is on tectonic plate boundaries, and our sort of usual activity is to run global models, both of Earth and other planets. So I'll start off by talking about the problem with generating plate boundaries in global models, but then sort of how we do it and some of the successes of our global models. Then I'll move to the influence of melting and crustal production on these types of models, and finally talk about some application to other planets, assuming that there's time. So again, we're sort of focusing on convection in the mantle, but it's important to realize that plate tectonics is really part of that convection, particularly the oceanic plates, which are essentially the cold boundary layer of the convective system, so created at ridges and going back into the mantle at trenches. And the whole system is powered by a mixture of radioactive heating and just cooling of the planet from a hot start. So, but it's challenging to understand plate boundaries, as perhaps you've been hearing in earlier talks. It's a multi-scale problem, both in length scale and time scale. So length scales from millimeters, sort of the width of faults, to thousands of kilometers, which is the dimension of the system, and time from seconds, that's earthquakes happening on timescales of seconds, to the billions of years that we're interested in modeling. So this means that if we're trying to model this, then in terms of resolution in time or resolution in space, there's really no limit to what we could use. Practically, one of the challenging things is to deal with the rheology, which is how basically how the viscosity is dependent on various things. Firstly, it's very dependent on temperature. It's also generally non-linear. There are also non-viscous modes of deformation, such as brittle failure and plasticity. And elasticity, of course, is important on short time scales. All right, so this is just an illustration of this variation in time scale. So if we go to the local mountain range, we can see sort of faults that are very narrow, and we see compositional sort of layering of the rocks. Here we see a fold, and yet we're trying to model a system with a scale of thousands of kilometers. So it's not clear how to deal with all of this small scale stuff in these large scale models. And focusing on viscosity, it's generally thought that rocks have a viscosity that depends on temperature as something like this. So an activation energy divided by kT, T is temperature. And in the laboratory, people measure the activation energy for olivine, one of the most common rock-forming minerals. It's about 340 kilojoules per mole. So we can calculate the temperature drop across the lithosphere, or sorry, the viscosity drop. The temperature in the asthenosphere is about 1600 Kelvin. The temperature at the surface is about 300. So if we put those into this formula, then we get a viscosity variation of about 48 orders of magnitude, which of course is huge. And actually non-viscous modes of deformation become important at the surface. So it's not actually as large as this. But if we put this type of viscosity variation into a model, then of course the cold lithosphere becomes completely stagnant or rigid, and we just get convection below it. So this is the stagnant lid, also known as rigid lid style of convection, just a global non-deforming or very slightly deforming lid with convection taking place below it. So this is the sort of expected style of convection for a planet. Somehow the Earth is different. Here's a numerical model that just illustrates this style of convection. So this is temperature, you get convection below this very highly viscous global lithosphere. And you can also, I don't know why the animation is not working anyway. It's not, oh, there we go, it's working now. So this illustrates the changing convective pattern below the global lithosphere, but basically the lithosphere is barely deforming itself. All right, so the next thing to ask is what happens actually when you deform rocks at different pressures. So this has been studied in the laboratory. This shows the maximum stress that a rock can endure as a function of the confining pressure. These are the actual experiments in the top graph here. And this is a sort of summary. But what happens is that at low confining pressure, then the rock breaks at some differential stress. Then at intermediate confining pressures, you get lots of small cracks, so-called microfracturing, semi-brittle mode. And then at higher confining pressure, the rock starts deforming sort of plastically. So that's ductile plasticity. So this shows that the rock does have a finite strength. So we perhaps need to take this into account in our numerical models. And of course, this consideration has led to the strength profiles that you see of the lithosphere published in various places. So the oceanic lithosphere is thought to have a strength profile like this. At low pressure, you get a frictional increase of maximum differential stress, limited by the friction on faults. At great depth, you're getting sort of viscous creep in the mantle, and in between, you get this ductile sort of yielding, as we see in these laboratory experiments. And in continents, you may get something similar, but it's a bit weaker, and sometimes you may get multiple strength peaks due to different compositional layers. And then when we put that in a numerical model, we can actually get convection where the lithosphere breaks up into multiple plate-like features. So that's what we're seeing on the left here. Purple is weak, and yellow to, well, green to yellow to orange is strong. So what we're seeing here is some strong plate-like features separated by weak plate boundaries. So just introducing this plastic yielding representing the finite strength of rocks is enough to give you some plate-like behavior in these global numerical models. However, the actual strength you need to put in, expressed either as a friction coefficient or a yield stress, is less than what is measured in the laboratory by roughly 1 order of magnitude. So in the laboratory, if we go back, we're measuring maximum differential stress of hundreds of megapascals, but in the numerical models, you need to put in about 1/10 of that to get the mobile lid mode. So there's obviously something that's not completely understood here. So this gap between the numerical models and the laboratory experiments. Nevertheless, if we use these lowered values, of the material strength in these models, we can get things that look quite like the Earth. Here, for example, we see a spreading center. We see the plate gradually getting thicker as it goes towards something like a subduction zone. So it's somewhat plate-like behavior. And we then have applied this to, for one thing, look at the age distribution of oceanic floor. Now, this is from data. This is not one of our models. And it shows the age of the oceanic floor from 0 to 280 million years as a function of position. Then you see that there's a lot of young oceanic floor. And as you go to greater ages, there's less and less of it. And when you plot a sort of histogram of the age of the oceanic floor, this is age, and the amount or the area, you get a roughly triangular distribution. In other words, there's a lot of young oceanic floor and progressively less as we go to greater ages. So this is roughly triangular, not perfect. And this may be surprising because if you think of a simple system where plates are created at spreading centers like this, and they move towards subduction zones like this, then we would expect a flat age area distribution. So we're roughly equal amount of oceanic floor of all ages. So together with Tobias Rolf and Nicholas Coltes and Stefan Labrosse, we looked at this. Here's a model that was run by Tobias Rolf, similar to the model I showed before, but with the addition of continents. So there are 6 very idealized circular continents on this, and they sort of influence the whole thing because there's a greater tendency to have plate boundaries, particularly subduction zones, at the edge of the continents. So this was published in 2012, and the left panel shows what I showed before, the triangular age area distribution of the Earth, and the panels B and C show models. And I draw your attention in particular to panel C, which shows several models which have different numbers of continents. And these models display a roughly triangular age area distribution. Whereas if we look at panel B, then models with only plates but no continents don't really fit the observed distribution. Models with only continents but no plates, that means also no temperature dependent viscosity, so the lithosphere is just weak, also don't fit. So it seems we need 2 ingredients to get this triangular age area distribution. That is strong plates with plastic yielding to allow them to break, and mobile continents. And then we can get something that sort of fits the Earth. Now, just to analyze why this is, why isn't the distribution flat? Well, there are 2 things that can contribute to a non-flat age area distribution. And the first is the geometry of the plate boundaries. So if the spreading centers and subduction zones are parallel to each other, then of course we expect a flat distribution. But as soon as these subduction zones are at an angle to the spreading centers, then we get a triangular distribution like this. And if these subduction zones are curved, then the area age distribution would also be curved. The second factor relates to the time dependence of the spreading rate. So if the time dependence is constant, then you might expect a flat distribution if you have this type of geometry. However, if at some point the spreading rate increases, then you will be producing more young oceanic floor and getting rid of the old oceanic floor more rapidly. So that can also lead to a triangular age area distribution. So now let's do some other comparisons of the real Earth as reconstructed by plate reconstructions over the past 200 million years with models. These are snapshots from plate reconstructions in the past. And these are the associated area age distributions. So you see that it hasn't always been triangular. Sometimes it goes up and down. Sometimes there's a sort of curvature like this. And when the numerical models are analyzed, it's also possible to find times that show these different area age distributions. So flat and then decreasing, sometimes triangular, sometimes with a curve. So yes, there seems to be similar variation displayed in numerical models as displayed in the real Earth. So that's reassuring. The next thing to look at is the size of tectonic plates. The plates are not all the same size. There's a distribution of sizes. In fact, there are more small ones than there are large ones. And that's interesting because simple convection tends to give convective cells that have a characteristic size. So somehow the plates are not displaying what we would expect from a simple convection. And this was studied in a paper by Mallard et al., including myself, in 2016. So Claire ran various global models with temperature-dependent viscosity and yielding that gives plate tectonics, and varied the yield stress. So this is the stress at which the rocks, well, basically yield, as discussed earlier. And what we see is that as the yield stress is increased, the size of the plates also tends to increase. So low yield stress here, increasing the yield stress gives larger plates. So to analyze this in more detail, Claire came up with some algorithm to actually extract the plate distribution from these numerical models. So this is the age of the oceanic lithosphere in the model. He found an automated procedure to find the plates and hence to find their size. And then these are plots of the cumulative plate count, so the cumulative number of plates versus plate size in square kilometers. This is actually log 10 of the plate size. And the dashed line here represents the Earth. This is the Earth-like size or number size distribution. And the colored lines represent various numerical models, or actually the same numerical model at different times. So for a low yield stress, you get too many small plates and not enough large ones. And then as the yield stress is increased, the plates generally get larger until when you reach 200 megapascals, you get a best fit to the Earth distribution. So yes, by adjusting the numerical yield stress, it's possible to come up with a size distribution of plates that matches that observed in Earth, which is reassuring. Now, looking at the models in more detail to see where the small plates form, it turns out that they tend to form where the plate boundaries are curved. So when you get a curved, a highly curved plate boundary, you can form lots of small plates in that area, as illustrated by these sort of zoomed in shots from the global models here. Okay, well, something that's not apparent in these models perhaps, but when you do a cross section and zoom in, is that the subduction zones are not very realistic. Typically, but not always, they're double-sided as shown here, which is that the oceanic lithosphere is converging from both directions and goes down, forming a sort of double thickness slab that is sinking more or less vertically to begin with. So despite this sort of lack of realism, the observations that I mentioned are still able to be fit. But what can we do about this? And one thing in these global models is that they typically assume that the top boundary is flat, using a so-called free slip upper boundary. But this can create unnatural geometries at subduction zones. Real subduction zones are not flat because the oceanic plate needs to bend as it goes down, creating a trench. And here's a typical sort of cartoon from a textbook about this. So it bends down, you get a trench. So if this trench is not allowed by forcing the topography to be flat, then perhaps the behavior of the system is not natural. And so let's look at some numerical models that allow the top boundary to deform vertically, as illustrated here. So this is from this benchmark paper. Now we see the subducting plate going down quite naturally, and we see a trench at the corner here. The same type of behavior can be obtained in the model on the left, which is using so-called sticky air, a layer of weak, low-density material at the top. So we then ran some models, some global models, to determine the influence of this. The top models here have the flat surface, the so-called free slip surface, and you get double-sided subduction, like I showed earlier. On the other hand, when you apply a more realistic free surface, then the subduction is single-sided, like in Earth. And to get the best, most realistic subduction, one needs both a free surface to allow realistic bending at the trench and weak crust between the oceanic plate that's going down and the overriding plate. And this allows decoupling of the subducting plate and the overriding plate, giving the most realistic subducting behavior. One can also do global models with a free surface and a weak crust, and one also gets sort of realistic looking single-sided subduction. So these seem to be the important ingredients for getting single-sided subduction: is a free surface and weak crust between the downgoing plate and the overriding plate. And this seems reasonable because you get a lot of sediments, they're hydrated. Also the oceanic basalt crust of the basalt is hydrated, and when it goes down, it's weak, and sometimes the water can be released, making it even weaker. So far, the models that I've shown are all of the same composition. They're not taking into the account that you can get different compositions, except for the weak crust, which I just mentioned. So now I'll go into the influence of partial melting and the subsequent or resulting production of crust. And here's a nice illustration of why this happens. This is the solidus of pyrrolite, sort of average mantle composition as a function of depth. This is a typical mantle geotherm. So below the lithosphere, it's adiabatic, more or less. And then in the lithosphere, it goes from the surface temperature to the asthenosphere temperature. And there can be this region where it overlaps the solidus, meaning that partial melt is generated. And much of this partial melt would then make its way to the surface where it erupts, forming crust, so basaltic crust. And so this shows sort of lithosphere structure when you don't have melting and crustal production, and when you do. When you do, you get this basaltic crust. So we have run over the years quite a lot of models in which you get this partial melting and production of oceanic crust. This is from Nakagawa and myself, 2012. So red here is basalt. So you get basalt production at the surface, or in the asthenosphere, sorry, it produces crust at the surface. Much of this crust is then subducted, and some of it can segregate into a layer at the bottom. And so you see these piles of subducted crust at the bottom, perhaps matching features that are seen in seismic tomography. But what effect does this have on plate boundaries? And so, Diogo looked at this during his PhD. And we see here model A does not include melting and crustal production, and it's in this stagnant mode the whole time, so stagnant lid mode. But when magmatism and crustal production is switched on, the model now displays episodic plate tectonics. So this illustrates that adding this melting and crustal production can actually cause plate tectonics or facilitate plate tectonics when otherwise the model would not have plate tectonics. And Diogo came up with this regime diagram. On the horizontal axis is the yield stress. And then we get different modes existing as a function of yield stress. At high yield stress, you get the stagnant lid. At low yield stress, it's mobile, which is plate-like behavior. And in between, you get some in-between mode. But when you add melting and crustal production, now mobile lid behavior can exist at a higher yield stress. So it makes plate tectonics easier, in other words. And this must be due to the, well, one effect at least is the stresses that are due to the varying thickness crust. The crust has a different density. It varies in thickness. This produces stress, which adds to the stress associated with the convection, making it easier to initiate plate boundaries. Here's a movie made by Diogo showing a typical episodic behavior. So this is a model that alternates between plate-like behavior and stagnant lid. So now, for example, it's in a period of stagnant lid. Then if we wait long enough, you see subduction, see lots of subduction taking place. Now it's stagnant lid again. Now we see subduction again. This is a mode that exists between stagnant lid and mobile lid, episodic plate tectonics. Okay, now in these models, it is assumed that all of the melt that's produced in the asthenosphere erupts at the surface to form crust. So-called extrusive heat pipe magmatism. And this tends to result in a cold and strong crust and lithosphere. So the melt is removed from the interior, it goes to the surface and immediately cools to the surface temperature. So it's cold and strong. Whereas on Earth, people usually think that most of the magmatism is intrusive. So magma ends up in the crust instead of at the surface. And hence this magma would warm the crust and make it weaker. So we would expect a warm, weak crust and lithosphere if there's a lot of intrusive magmatism. So indeed, Diogo tested this during his PhD thesis, and here's a movie which is the same as the previous one, except now that 90% of the magmatism is intrusive and only 10% is extrusive. So now we see a different tectonic style. Now there's sort of dripping of the crust, which is red here. Red is basaltic crust all the time. So instead of being episodic, as it was with pure extrusive magmatism, now the lithosphere is generally weak. We're getting a lot of dripping of crust and the surrounding part of the lithosphere right from the beginning. So we're getting a warm, weak lithosphere. And then later on, as things cool down, it becomes stronger and we tend more towards conventional subduction. But let's now just go to the regime diagram. So it's published in 2020. And what do we have here? So here we have different regimes plotted as a function of yield stress, like before, and extrusion rate, where at the top, it's pure extrusion, so everything erupts. And at the bottom, it's pure intrusion, all melt intrudes. And what we see is that for high extrusion, we get the same modes as before. At low yield stress, it's mobile, plate-like. At high yield stress, it's stagnant. And then in between, it's episodic. But when you have a lot of intrusion, so 80% or more of the melt intrudes, there's this new mode, which we have named plutonic squishy lid. And this exists regardless of the yield stress. So it doesn't depend on the yield stress. You can have this squishy lid, which is facilitated by lots of intrusion all the time. And here's a cartoon to illustrate what's going on, because sometimes the numerical models are a bit unclear. So what happens is that intrusion happens in some areas, not everywhere. It happens where you get upwellings that are warmer than average. And this creates weak areas of the lithosphere. And what you can get is horizontal movement of the lithosphere between nearby weak areas. So this is what's happening during this plutonic squishy lid mode. Now, other groups, including my close colleague here, Taras Guryar, and his co-workers, have done local or regional models relevant to this. So now this is modeling the top 200 kilometers of the mantle, not the whole mantle. And yes, this is for early Earth when the mantle was hotter than it is today. And they get something that's compatible with this plutonic squishy lid mode. So they also find a sort of weak crust with some partial melt inside, a sort of weak lithosphere, again, lots of partial melt in the asthenosphere. Other groups have done subduction models in which they increase the temperature of the mantle, and they have found that you cannot get Earth-like subduction when the mantle was hotter, as it was billions of years ago. And here's another example of a regional early Earth model showing that you get a lot of melting, you get a weak crust, and you get delamination. So the similarity of our globals to these more highly resolved regional models gives us some confidence that what we're seeing is real and not just due to low resolution. So let's summarize the tectonic modes that we have seen so far. There's the mobile lid, which is the plate-like mode, stagnant lid, would be a sort of Mars-like mode, and alternating between them, episodic lid. And then there's this new mode that I just described, plutonic squishy lid, when all of the melt erupts, you get a so-called heat pipe mode. And something that I haven't talked about is that it's also possible to get a mode where you get spreading centers, ridges, but not subduction zones. So now let's apply these concepts to some other planets, starting with Venus. Now, Venus clearly doesn't have plate tectonics today. We don't see spreading centers. We don't see like a global network of spreading centers and subduction zones, but people have identified some features on the surface which can be interpreted as subduction zones. So there is some evidence for subduction in some areas of Venus. Also, when we look at the surface, we see a highly deformed surface, particularly in some areas. So clearly there is deformation of the crust, i.e. tectonics, but it's not plate tectonics. We can also see cracks like faults. So we see faults, we see distributed deformation, we see volcanoes and some other likely volcanic features called coronae. So, and we also see that the surface age is in the range 500 to 700 million years. So there have been various proposals for why Venus has a roughly uniform surface age. One idea is that there was a global overturn that long ago. Extending this, perhaps the lithosphere of Venus overturns episodically. Perhaps Venus is in this episodic plate tectonics mode. Sort of adding to this, or supporting this idea, is that it's actually difficult for a planet the size of Venus to lose its internal heating in a stagnant lid mode. It would just heat up and heat up until there's massive magmatism. In fact, to lose, if Venus has the same concentration of heat-producing elements as Earth, and if it loses all of its heat through magmatism, you would need about 10 times the amount of magmatism that you get on Earth in order to lose all of that heat. And that is not observed on Venus. So that is evidence that maybe Venus has some sort of episodic plate tectonics, which allows it to lose its heat more efficiently. It has also been suggested that this plutonic squishy lid mode could be applicable to Venus. It seems to fit the observations of surface deformation. Now, we have done various models of Venus, starting in 2012 and actually ending in one that was published recently. And this model shows clearly the episodic overturn mode. There are long periods of stagnant lid behavior, punctuated by sort of global overturn of the lithosphere. And this movie is running quite slowly. Maybe we'll wait for one more overturn. There we go, that was another overturn. And here's a 3D version that was in 2 dimensions. So you see stagnant lid behavior punctuated by vigorous global overturn. Now, if we zoom in at what happens during one of these overturns, this was by Kramarian myself, you see that an overturn normally starts in one place. You get a sort of crescent-shaped subduction zone, and then propagates. So you get these sort of rollback of subduction zones from the initial place until basically the entire lithosphere is subducted, and then it grows again by conduction. So our latest published paper on Venus was published only a few months ago by Jia Cheng, myself, and Diogo. And what we were doing is trying to include a more realistic rheology for the crust and intrusive magmatism, which I already mentioned the importance of. And so this is motivated. So normally in global models, people assume the same rheology for all different compositions. And that's not realistic. The crust, the basaltic crust, has a different rheology than that of the mantle. And of course, also the continental crust has a weaker rheology again, although I won't be showing models with continental crust here. So what we did is use a more realistic, a weaker rheology for the basaltic crust than for the mantle, with the mantle being based on olivine. And then you get an evolution that looks like this. So this is the composition and temperature at different half-billion-year intervals through the model history. At this level of detail, it looks actually similar to the earlier models. You get episodic global overturns and stagnant lid in between. But when you plot it in a different way, when you plot the surface strain rate as a function of time and compare the models with a weaker crustal rheology to those with an olivine crustal rheology, then you see a big difference. You see that the strain rates on the surface are orders of magnitude higher than they are with the olivine rheology. And in fact, the ratio of the surface velocity to the velocity in the interior is of order 1, meaning that the surface is deforming a lot and the velocities are sort of similar to the interior velocities. Perhaps matching sort of the observations of widespread deformation of Venus's surface. So we call this the deformable episodic lid mode. because there's still this episodic overturn, but in between the overturns, there is quite a lot of deformation. Now, another thing that can happen in these models is that you can get a widespread magmatic resurfacing, even if the lithosphere itself does not go down. So depending on the parameters. So I won't talk about this very much. So anyway, the deformable episodic lid mode is sort of now our favorite mode for Venus. Episodic overturns with sort of some surface deformation in between. So finally, let me talk about planets elsewhere, not in our solar system. And so far, about 5,000 of them have been discovered, so-called exoplanets. The number keeps rising. Currently, it's about 5,000, as I mentioned. And it's useful to plot these on a graph of size relative to Earth. So this is Earth size. You see the Earth on the right, to orbital period. So this is how long they take to orbit their host star. Earth takes 365 days, so it would be over here somewhere on this diagram. So what we see is that planets of a wide range of sizes have been discovered, ranging from smaller than Earth to larger than Jupiter. And most of the ones that have been discovered have a fairly low orbital period. And this is mainly because these are the ones that can be found. It's much more difficult to find planets that have a longer orbital period. And it's useful to classify these planets into different types. Not all of them are rocky. Many of them are Jupiter-like, either hot or cold. Many of them are Neptune or Uranus-like, so-called ocean worlds and ice giants. But quite a lot of rocky planets have been discovered. So it's interesting to think about these and whether they would have plate tectonics. And they have a range of sizes from smaller than Earth to larger than Earth. The larger than Earth ones are called super Earths. Here are some of them that are potentially habitable, meaning that they might have liquid water on their surfaces. Of course, the detailed images are artists' impressions. All we actually know is their size and their mass. So over 10 years ago, we did a study to predict whether larger planets that are otherwise similar to Earth are more or less likely to have plate tectonics. So I won't maybe go through all of the details, but this is the simplest type of planet you can imagine. The physical properties are constant except for viscosity, which is dependent on temperature and stress. And we considered planets that are internally heated by radioactive heating, planets that are heated from below by having a hot core, and then different types of yielding, either constant with respect to pressure, which is appropriate at higher pressures, or proportional to depth, which is appropriate at lower pressures. And we came up with analytical scalings and compared to numerical experiments. And they agreed with each other. So if for an internally heated planet, if you go from a small planet to a big planet, it's the same. If it's basally heated, you go from a small planet to a big planet, it's actually more likely to have plate tectonics. And the numerical experiment and the scalings agree. So we predict that plate tectonics is equally likely for internally heated convection on larger planets, or more likely for bottom heated convection. And some more complicated numerical models that we have also run since then seem to agree with this. Okay, so now let's sort of sum up, trying to put all of these different regimes on the same diagram. So various regimes are possible. Some of them have plate boundaries. some of them do not. So let's start with the Earth, which has plate tectonics. Then there are other regimes possible. Squishy lid is one I've focused on. It's related to this deformable episodic lid, except that it's episodic. This is where you have a lot of intrusion. You get more distributed deformation. Now, if you have even more magmatism, if the interior is even hotter, there's likely to be widespread partial melt in the interior. And this corresponds to the planet, or the moon, actually, Io, one of the main moons of Jupiter. And then, well, early on in planetary history, there was a lot of magma. The outer part, or maybe the whole body, was likely to be molten, so-called magma ocean phase. Then, when you go to a planet like Mars, you obviously don't have plate tectonics. That's in a single lid mode. There's some tectonics. You see a rift valley, for example, and you see several volcanoes. So we call this a sluggish single lid. And then when you look at a body like the moon, its surface or lithosphere is completely dead. This is a pure stagnant lid body. So to conclude, combining a yield stress with temperature-dependent viscosity can generate plate tectonics in global models. These models can nicely explain the triangular age area distribution of Earth's lithosphere, and can explain the size frequency distribution of Earth's plates. We have found that including melting and the resulting compositional variations, basically crust, can play a large role in the tectonic mode and can generate new modes of tectonics that you don't get with purely thermal convection, particularly the plutonic squishy lid mode, which seems to explain early Earth and modern day Venus. Looking at other planets, Venus, we think, has this deformable episodic lid mode, which is something like the plutonic squishy lid mode with episodic overturns. And super Earths, we predict, are more likely to have plate tectonics than the Earth, other things being equal. In other words, the surface temperature, the presence of water at the surface, and so on. Okay, well, thank you for listening, and I'm happy to answer questions.
Well, thanks. So thank you very much. I do not see Catherine. Catherine, are you there? I mean, she alerted me that there might be issues with her internet. So I'm anyway acting as a co-host. So thank you very much, Paul, for this exciting talk. This is really, really informative and extremely interesting for us. So I think that I opened the floor for questions. And if you have questions, please unmute yourself, introduce yourself, and then unmute yourself and ask your question. Otherwise, you can write it on the chat, and I will read it for you. So in the meanwhile, I have a question, Paul. I mean, looking at the different tectonic modes, and since you're looking at two different planets like Venus and Earth, I mean, if we use, I don't know whether within your models you could generate topography, and I understand that the topography of Venus and the topography of the Earth, I'm not an expert in this, it might be different. So to some extent, I mean, do you think that this could be used as an external constraint to see which is the leading mode and in between the two? And I'm wondering whether you account for, I mean, since the surface temperature seems to be, I mean, do you think that these models could be coupled with the atmosphere at some point?
Yes. Yeah. Well, there are two questions there, I think. So the topography, yes, is different between Venus and Earth. If you plot a histogram, Venus's topography just has one peak, whereas Earth's topography has two peaks corresponding to the oceans and the continents. But even the continent in the topography in Earth's oceans is different. And this is actually something that Diogo is working on at the moment. And yes, without going into details, it should be possible to tell the tectonic mode by looking at the histogram, or topography. And the second question was coupling with the atmosphere. Yes, and this is something we have worked on for Venus. Indeed, there is several papers by Cedric Gilman and myself, and sometimes others, and Cedric is also tuned in here, which couple the atmosphere of Venus to the interior, which outgasses. Now, currently we're working on implementing a more complete atmosphere model. Venus's atmosphere is basically just carbon dioxide with a little bit of water that can be important. But even though we did find with Cedric's models that the coupling can be important. When water outgasses, then it creates a bigger greenhouse effect, changes the surface temperature, which can change the tectonics.
Right.
So yes, the surface temperature can change the tectonic mode. So now we're working on implementing this for that can also cover more Earth-like planets. Because obviously in Earth-like planets, you can recycle carbonate and water, whereas in Venus, that's going to be much more limited or not at all.
Interesting. Thank you very much. That's interesting. So Alik has a question. Please unmute yourself.
Yeah, hi,
Ali.
Paul. It was a quite interesting. I mean, the review, wonderful. I really enjoyed the part related to the squishy lead mode. And I have a few questions because you specifically distinguish between the intrusions and the extrusion. Normally, big these large igneous provinces are, they have two modes. They have a lot of extrusion, but at the same time, a lot of intrusions like seals and normal intrusion. Is it possible to clearly understand, not as a two end members, but to see how, in this case, it works? Not just a fully taking out, but this placing. You mentioned about some intermediate, I mean, it's a mode, but again, I understand that it's you change the rheology of the crust in this case, correct? And if you change the rheology when you're speaking about the weak crust, what is really weak crust in terms of the rheology? How you change it with respect to the normal, let's say, crust. And another things, observations, which my observations, maybe it was not correct. I observed that generation of the, let's say, plumes or some upwellings, not goes really quite to the top layers of the, let's say, to the bottom of lithosphere. Specifically in these models, what happens to, why the mantle upwellings not penetrate the through mantle to the top of the lithosphere? What prevents them to do it? I see that it's, let's say, in the middle layer, they go in some way to the middle, let's say, mantle, but not it's up. Yeah, thank you very much for clarification.
Okay, well, thank you, Alec, for I think it was 3 questions. Anyway, so yeah, extrusive versus intrusive is something we well, our models include both. So, but we have to at the moment specify the ratio sort of as an input parameter. So what it would be good to do is have that arise self-consistently, based on some, I don't know, the strength of the lithosphere or the buoyancy of the magma, or some people have proposed various hypotheses. And so yes, we would like to develop some sort of criterion for determining more self-consistently what fraction of the melt erupts and what fraction intrudes and at what depth it intrudes. Presently, we also specify in advance, does the intrusion take place at the base of the crust? Does it take place in the middle of the crust? This type of thing. And as for the rheology, well, the crust is weakened through one of two effects. Now, in the first, the earlier models I showed that Diogo did, the crust is weakened only by the warming up caused by the intrusion. So you intrude magma at the base of the crust or in the middle of the crust, and this warms the crust up, so it just has a lower viscosity because of that. In the last models I showed for Venus that we recently published, we're actually using different creep law parameters for the crust. And we're taking basically a plagioclase rheology, because people are often using that when they're modeling the crust. That's sort of an end member, because basalt is not made purely of plagioclase, it's about 50% or so. And as for plumes, yes, you're quite right. In the more complicated models we do that include various compositional effects, such as this one, the plumes typically don't go all the way from the bottom to the top, but instead they're sort of deflected at the 660. And that's due to this so-called basalt barrier effect, which was first identified by Davies. Well, let's just take a step backwards. It's been known for decades that there's an endothermic phase transition there, which even on its own tends to inhibit slabs and plumes from going across. But it probably doesn't inhibit them completely on its own. When you add the compositional dependence of that, which is that in basalt, the transition to the lower mantle composition occurs at a greater depth, leading basalt to be positively buoyant for some depth range between about 660 and 740 kilometers. When you add that, you can get quite strong layering. Mm-hmm. And we see here, actually, there's a lot of basalt trapped in the transition zone. And it's this that's sort of preventing plumes from going through from the lower mantle to the upper mantle. Mm-hmm. But you can get then upper mantle plumes, which start from the transition zone and come up and cause some magmatism.
Yeah, thank you very much. That's great. I didn't just look at, because there's so many information. Yeah, these here are really the barrier. Yeah, I see. Thank you.
Any more questions? Please feel free to ask questions. I mean, Paul has put it so simple that it was really understandable for. Thank you so much. I think that Catherine is popping up again.
Yes, from the rooftop. Sorry.
That's fine. Well, a nice view in Rwanda.
Yeah, I could show you Kigali, but it's very hazy today. Sorry, I was just totally the mess, totally offline.
Paul, while waiting for other questions, I mean, I have just a curiosity. I mean, on still the comparison between Earth and Venus, in which discussion about plate tectonics here and there and not there. I mean, if the surface temperature in Venus is so high, I mean, would you be happy with a statement like this, that you would not expect any dynamic weakening to happen on those faults that are in Venus? I mean, they are mainly, I mean, all those big faults that might be there, I mean, would be sort of stably moving and not dynamically weakening?
Well, yeah, fault behavior is not my area of expertise, but it has been argued by Shunkarato and Sylvain Bardot that what you just said is the case for Venus. So that, at these intermediate temperatures, well, for Earth, they're intermediate temperatures, then you don't get earthquakes, basically. So they have argued that you don't get Venus quakes, you get sort of stable slip on faults. But that's not my sort of expertise. Because another difference is that in Earth, water probably plays a large role in weakening faults, both by forming hydrated minerals like some serpentinite and by reducing the normal friction.
Like talc.
Yeah, and that doesn't happen on Venus.
Venus. Very nice, very interesting. Catherine, if you have questions, but you've lost one part of the talk.
Yes, I lost one part. I'm very sorry. yeah.
So while we're waiting, I don't know whether there are any other questions. It was so well, I do not see any. So thank you very much, Paul. That was really nice. I don't know whether Catherine, you would like to say a few words before we close up.
Oh, I think I found the talk really great. Like now we know all the ingredients we have to put in our models to have something which can resemble plate tectonics. So yeah, thank you, Paul. It was very good. Very good.
Mm.
I'll have to watch the last part on the recording. Sorry.
Thanks.
Yeah, so if we end there, I would like not only to thank Paul again for his talk, and his time to preparing that, but also everyone joining us online and making this series kind of active. Okay, so yeah, thank you very much, everyone.
Cheers. I stopped the recording.
Yeah.